We are discussing question from GATE 2014 and it is based on the energy band diagram. So it says that an n-type semiconductor is having uniform doping. An n-type semiconductor having uniform doping. So this is a very important term, that the semiconductor having uniform doping. Now this semiconductor is biased, so it is biased using a battery. So this is the negative terminal of the battery and this is the positive terminal of the battery. And this n-type semiconductor which is having uniform doping is biased using this battery. Now it says that EC is the lowest energy level of conduction band and EV is the highest energy level of the valence band, and EF is the Fermi level. Then which of the following represents energy band diagram for this biased n-type semiconductor? Now if we have a normal semiconductor which is in equilibrium condition, normal n-type semiconductor, then its energy band diagram is like this. So this is a conduction band, this is Fermi level. Fermi level is very close to the conduction band and this is the valence band. So Fermi level is close to the conduction band and this is the energy band diagram for the semiconductor in when no external battery is applied, and this is for uniform doping. So in uniform doping, the gap between EC and EF is constant at every point. So this gap is constant at every point. So option A is for the n-type semiconductor without any external battery. So this is without any external battery, so this can't be the option. Now if we look at the option C, then in option C this gap between EC and EF is very small here, but it gets very wide here. So this option is also not possible because this cannot be possible in uniform doping, and we have been given clearly that this semiconductor is uniformly doped. So this is possible only for non-uniform doping, but it is given uniform doping, so this also can't be the option. So option A and option C can't be the answer. Now when we bias the semiconductor, then the energy band diagram moves downwards towards the positive potential. So the positive potential is at this point, so this point will move downward. So this is the correct option. This cannot be the option because the band diagram has moved downward in this direction, but this direction is negative and this direction is positive. So the energy band diagram will shift downward towards the direction where the positive potential is applied. So it will shift downward here because the positive potential is applied here. If suppose this could have, so the correct option here is D. The B could have been the correct answer if it was applied like this. The positive potential was on this side. If the positive potential was on this side, then B would have been the answer, because now the positive potential is at this side, so the energy band diagram will shift in this direction, will move downward in this direction. But in the question, the positive potential to us was given like this. So this is the answer because the energy band diagram will move downward in this direction. So D is the correct option.